Hi. So let's talk about the convolutional building block, the convolutional layer, the nn dot spatial convolution. It's not very modern in the sense transformers have kind of taken over for the most part, but it's still a building block that we should know about. And so let's spend maybe 20 minutes trying to learn about convolutions. Right. So what are convolutions and why did it come about? So the history goes back to the 60s and the 70s, but let's look at this example of an image. So let's say we have an image of size 200 cross 200 pixels. Right. Now what we usually do is we flatten it into a big vector. So 200 into 200 is 40,000, right? So it has these, let's say 40,000 input neurons, and let's say we want the same number of output neurons. So let's say we have these all the way to, let's say 40,000. So we have 40,000 input neurons, and then let's say we have the same number of, let's say, output neurons, 40,000 output neurons. And now let's say we have a fully connected layer between them, right? So a fully connected, as you know, is everything connected to everything and so on. Yeah. So what is the size of this layer? So what is the size of the weight matrix here? It's, as you know, 40k cross 40k. Right, so 40k cross 40k is 4 4s are 16, and then we have the 2 zeros, and then we have another 6 zeros, right? So it's about 1.6 billion, right? So I've written 2 billion. So it's about 1.6 billion parameters. So in this single layer we will have about 1.6 or let's say 2 billion parameters, and that's a lot of parameters, right? So for example, AlexNet, the network that changed deep learning forever, had about 60 million parameters, and in this single layer we are talking about 2 billion parameters. So that's not a good idea. Why? Because of multiple reasons. One, it's a waste of resources. It will start to overfit because we will usually not have so much training data. And two, especially when we are dealing with, let's say, images. So images are 2D where spatial correlation is local, right? What it means is there is something like a nose, and then there are eyes which are close to the nose, right? So there is this kind of a relationship. Or with, say, speech. Right, so when you have speech, the let's say sound at time t is correlated to the sound at t minus 1 and t plus 1. So cat, the a is related to the k and the t, right? So this is why it's not a good idea to just blindly put a fully connected layer, and I'll show you this again with another example. So what we can do instead of this fully connected, we can do something called as this locally connected. And what it means is, let's say we still have our 40,000 input pixels, and now instead of and we also have our 40,000 outputs, right? So we have 40k here, we also have 40k here, and now what we are saying is, instead of connecting one to all outputs, let's connect, let's say like these 10 cross 10 or 100 neurons to 100 outputs, right? So what we are saying is, okay, let's connect this to 100, right? Some 100, then let's connect the next one to another 100, then let's connect the next one to another 100, and so on. Right? So this way we are reducing the number of parameters. How much are we reducing it to? So we are connecting each of these 40k, right? Each of these 40,000 into 100 more, right? So we have so now we have this 4 million parameters, right? And so that's what I'm saying, that we have 4 million parameters when we do this locally connected. So what we are saying is, okay, we'll connect maybe this part to one neuron, this part to another neuron, so this part to another neuron, this part to another neuron, and so on. But now this parameterization is good when all your input images are registered, when the same part appears in the same region of the image. right? This is because what if it moves, right? What if, my eye is here, and so the neuron corresponding to the eye learns about the eye, but in another image we have, say, the eye here, right? So that part of the neuron did not learn about the eye. So then how can we mitigate it? So then comes this concept of convolution. But before I come to this, I want to explain this, right? What we talked about, this 2D spatial relationship has this correlation, meaning, let's say we look at this 4x4 image, right? And this 4x4 image, here we can clearly see this figure 4, right? So we, as a human eye, we can look at that and we say, okay, there is this digit 4. But now suppose we were to flatten it. Suppose we kind of take each row. So we take this first row and we put it here, right? So there's a white here and a white here, so a white here and a white here. Then we take, let's say, the next one, so 1 black and 3 whites, and we put it here. Then we take this 3 black and 1 white and we put it here and here. Now it has lost that spatial relationship. We have lost the spatial relationship between the neighboring rows, right? So this has that disadvantage that when we want to blindly flatten an image into a vector, it loses the spatial relationship between the different rows. Yeah. So instead, what we want to do in convolution is this concept of translational invariance. And what I mean to say is that the same parameters are shared across different locations of the image. Meaning, let's say you have, this is this convolution with kernels concept. So what I mean is, let's say we want to say that, okay, so we will connect, like in our previous example, let's say 10 cross 10 region with one output neuron, right? So this 10 cross 10 will give rise to this one activation, this one output, this one feature, this one, embedding, right? So this is what this output will give rise to, but then we will move this kernel. So this 10 cross 10 is called a kernel, and then we will move it a little bit, and then this, when we move it, we get another output, and that is the another output neuron, right? And we keep doing this. We kind of move it all over the image, and this movement is called a sliding window, because it's like, window sliding. So every slide, this slide is also called a stride, right? So it's the stride, like a human stride. So you can slide a little with the stride, and then you can slide again, and each of this produces one output and a single output, and it's usually just like a dot product, right? So, and in the next slides we'll talk about this in more detail, but the concept is what we want to understand, the intuition. Why did we go to convolutions at all? Yeah. So let's say, let's simplify it and let's look at convolution in 1D, and let's say our image has these 4 numbers, 1, 2, 3, 4. So these 4 pixels here, and let's say the kernel, the weights is this 3D, right? So this 3-dimensional vector that we have, and what we want to do is convolution. So all we have to do is this sliding, right? So we first overlap this here to this first thing, and then we slide it a little bit, right? We then do this, and then we simply do the dot product. So again, I'm drawing it here. So what I'm saying is, okay, in the first part, so 1, 2, 3, and 4. So 1, 2, 3, and 4. The first time I overlap, the kernel has size 3. So I do this, right? So 1, 2, and 3 of the kernel. Next time I overlap it here, 1, 2, and 3, right? So I moved it a little bit. I just moved it 1 pixel to the right, right? And what this does is, and every time I move it, I do a dot product, right? So what I mean is, when I do this into this, plus this into this, plus this into this. So 3 times, right? So this is exactly what I do. I1W1 plus I2W2 plus I3W3. Similarly, and that gives us the first output. Similarly, after moving it, I do the second output. So to create the second output, I do I2W1 and then I3W2 and then I4W3, right? And then these are all scalars, right? So my output is just 2 numbers, O1 and O2. And this is actually correlation because if you were to do convolution mathematically, it would look like this, but we don't need to worry about it, because in deep learning what we say is, if you look into this in detail, you will see that this is just a flipped kernel. All we do is a correlation with a flipped kernel, and in deep learning we say, okay, instead of flipping the kernel and doing all this, you can just assume that the learning process enables us to learn this flipped kernel. Meaning, if it were to learn something, it will learn the exact same thing with the convolution operation as with correlation operation, because it can just learn this flipped kernel. Think about it, right? What I mean here, because it's a little bit deep. But for now, what we just want to know is, when PyTorch implements convolution, it actually implements correlation. But for now, all practical needs, we just call it convolution. Okay, and when we want to mathematically write correlation, which we will call convolution, we just say O of I is this into this. Another thing we should note is the dimension of output will be less, because we didn't have enough space to slide, right? We could only slide 2 times, so we will only get these 2 outputs. And mathematically, what is the dimension of output? Is the dimension of the input minus the dimension of the weights plus 1. And remember this formula, right? Input minus weights plus 1. So this is something that you should remember. Okay, and now if you wanted to get the same sized output, you would need to do something called as padding. And in this sense, we do half padding, and padding is this operation of 3 by 2 flooring it, right? So our kernel size is 3, so we will divide it by 2 and then floor it. And this is what we need to do when we want to get the same sized output as our input, right? So we need to do this padding, and usually we pad it with zeros, and then you can slide it all over and you will get the same size output as input. So then you can also have this concept of stride, right? You don't need to kind of go with the stride of 1. You can always jump, and suppose we want to do a stride of 2 along with this half padding, and then the size of output. So here we jumped, right? We put it here, and then the next time we jumped here, right? And then we cannot go anymore. So we skipped this one, right? We did not come here, right? We did not come here. So, and then the size of output would be the same as size of input minus size of your kernel divided by stride, and then plus 1. But you can ignore this. You should just remember without the stride formula, right? I minus W plus 1. Now, this is really interesting, right? So here, let's do, the backward. So the forward is simple. We looked at it, and now let's mathematically do the backward, and let's see how cool, the gradient of loss with respect to the input is, and the gradient of loss with respect to the weights is. So, the formula for O1 is I1 W1 plus I2 W2 plus I3 W3. The formula for O2 is I2 W2 plus I3 W2 plus I4 W3. What is the Jacobian? Let's write, dO by di, and the Jacobian, as you know, is dO1 by di1, dO1 by di2, dO1 by di3, and dO1 by di4. Yeah. And similarly here, it's O2. So all of them are O2, right? O2 and O2 by I1 and I2 and I3 and I4. Yeah, and now let's just do this. So what is dou O1 by dou I1? Dou O1 by I1 is W1, right? So we write W1 here. Then O1 by I2. So O1 by I2, everything else will be 0, right? So the first term is 0, so I2 we get W2, then W3, and now let's do so the last one, O1 by I4. Now the first equation has no I4, so our last one is 0. Similarly, when we do it for 2, so we want to differentiate with different i's, right? Ij's, let's say. So when we differentiate it with, so when we differentiate with I1, there is no I1, so we get a 0. But when we differentiate with I2 for the second term, we get W1, and so on. Yeah. So just remember this. And now so this is clear, and now let's differentiate it with respect to W, and you know again the formula. So what is the Jacobian when we want to differentiate, you know, dou O by dou W? So it will be again O1. So let me just write the O1 3 times because we have 3 weights O1, and then this will be with W1, W2 and W3. Similarly O2 with W1 and O2 with W2 and O3 with W3. And now let's look at these quantities, right? So let's differentiate O1 with W1. So when we do O1 by W1, we get I1. Yes. So we got I1. Then O2 by W2, we get I2, right? And then with W3, we get I3. Yes. Because everything else is 0, right? When we differentiate with W3, the first terms are zeros and so on, because it doesn't depend on W3. Similarly, for the second row, when we differentiate this with different components of, let's say, Wi, we get I2, I3 and I4. Yeah. So let's just remember this. So we have our first equation, we have our second equation, and let's assume that the gradient coming in, right? So let's say this is our convolution layer, and the gradient coming in from this next layer, what is the size of output? The size of output is 2 cross 1, right? So its a size of output is 2 cross 1, and then the gradient coming in will be the same size as output, just that it will be a row vector, right? It's row vector of 1 cross 2, and let's assume this is the row vector, this is the gradient of loss with respect to the output, right? So this is the gradient of loss with respect to output that is coming in from the next layer, that we are given by the next layer, so that we can continue with our chain rule, right? So that we can continue with our backprop. So when let's assume that we are getting this from the next layer, and now let's write out the formula for derivative of loss with respect to the weights, and you know it's just derivative of loss with respect to output, which is coming in from the next layer, and derivative of output with respect to weights, which we calculated here, right? And now when we do this, when we multiply it, so this is a matrix, this is a vector, we multiply it on the left, right? So what we do is we do dou LO1 and dou LO2. We want to multiply it with this, right? So with this one, I1, I2 and I3, and then I2, I3 and I4. So it's, you know, this is 1 row and 2 columns, this is 2 rows and 3 columns. So finally what we get will be 1 cross 3, right? So it will be a column vector of size 1, sorry, it will be a row vector of size 1 cross 3. Yeah, but this is the gradient with respect to the weights, and with this we can update the weights because the size of weights is also 3. And now if we were to just multiply it, right, so it's this into this plus this into this, right? It's just this into this plus this into this. So this is exactly what I've written here, right? And now similarly for the second term and similarly for the third term, you can also think of it this as a dot product of this with the columns, right? So when we are multiplying it with the column vector on the right, it is dot products with the rows, but when we are multiplying it with a row vector on the left, it is dot product with the columns, right? So these are the dot products of, let's say, this vector with the 3 columns 1, 2 and 3, right? So for example, let's look at the last one. It's dou LO1 into I3, right, plus dou LO2 into I4. Yeah, so it's simple, but now this is the fun part, right? So let's see what this becomes. So if you were, so you can also think of this as again a correlation operation, or you know, if you want to use the normal lingo, let's say just convolution of the gradient that we got in from the next layer with the input. Because if we do this and we do this convolution, if you just slide it, let's see what happens. We get so we get this, right, I1 LO1. So we get this I1 LO1 into I2 LO2. Then we move it, right? So then we move it here. So then what do we get? I2 LO1, so I2 LO1, and then I3 LO2, and similarly the last time when we do this operation, we get this LO1 I3, right, and LO2 I4. And this, so then you can simply write this as a correlation. The derivative of loss with respect to weights is just this correlation of your inputs with the loss, with the gradient of loss with respect to the output that is coming in from the next layer. So you just have to write this correlation, the correlation function once, and you can then use it to then also compute your backprop. I will not go into detail, but your derivative of your loss with respect to input, the gradient that we need to pass to the previous layer, also kind of is a correlation operation. It's a correlation operation with your weights and the flipped gradient that is coming in from the next layer. We don't need to do this, but what you should know is, the backward of a convolution operation is also a convolution operation, and this is pretty fun. Yeah. So now we've done majority of it. We just want to look at how to do this, let's say in PyTorch. So we're going to look at that along with your TA in your office hours and as homework. But for now, let's just look at so let's do this in LuaTorch, so that I don't show you the exact code, so that you get the chance to write it yourself. So what I have here is we are calculating, so again, so we'll talk about the spatial dimensions in a bit, but so let's talk about the spatial dimensions and then we'll come back to this. Yeah. So yeah. So we have spoken about this, and now what we want to do is, usually we're not doing this 1D convolution, we're usually doing this 2D convolution. And when we do this 2D convolution, it looks a little bit like this, right? Usually we have these 3D kernels, and then we move this 3D, slide this 3D kernel around in our input. But now let's look at this with more detail, and let's look at this with a very concrete example, and then we will understand convolution once and for all, trust me. So let's look at a more general case, right? Our general case, our input is two-dimensional, right? In the sense it's both height and width, and it also has some depth. What do I mean? So this thing has depth, meaning it has two channels, right? So this is not a single channel image, it's, let's say, a two channel image, right? So our first channel, you can see here, of size 4 cross 4, but then there is also this second channel, right? This thing that we have here, this is our second channel, and this is what sits here. Okay, so this is what I wanted to show you with this visualization that we have, right? So usually, so instead of 3, we have 2. And this kernel, this is the kernel that we will see here, right? And so now you have to remember this, but your input has some channels, right? And you can do nothing about this because this is that you already have in your input. But you can choose how many channels you want as output of this convolution operation. So in this case, we choose 2. Okay? And then we can also choose the size of our filter. We choose 2 cross 2. Okay, and these are the only things we can choose, right? We can choose the number of output channels we want. In this case, we chose 2, so the first one and the second one, and we can choose the size of our kernel. In this case, we chose 2 cross 2. But the size of your weights will actually be the number of input planes, the number of, so that this is the number of output, the number of input, height of the kernel, width of the kernel. This you have no control over. Yeah. Suppose there were, instead of 2, if we had, let's say 3, we had another one, or let's say we had 4. So here I'm drawing 4, right? Let's assume we had this 4 channel input. In this case, this one, right? This one would be 4. Yeah, this we have no control over. So now let's look at our case, which is 2, because we have 2 channels as output. Our size of our weights, the size of the kernel, you can imagine. So suppose I were to draw it, right? It would look like this, because what is our input looking like? Our input looks like this. Yes. And what is the size? It's 4 cross 4. 2, 3, 4, right? Yeah. So 4, and this is what our input is looking like. Now our weights have to look like this, right? So we chose our height and width. Our height and width are 2, right? this is the height and width, but we cannot choose our depth, right? So let's just do 2, right? We cannot choose our depth because it has to fit in here, right? What I'm trying to say is, okay, let me also draw this 1, 2, 3, 4. So this is the size of our input. So it has to fit here, right? So this kernel that we have, it has to fit here. Yes, it has to fit in this area, right? And this is what we are doing when we are kind of fitting this in here. Yeah, and then we're doing a dot product of this whole thing. What do I mean by that? We mean that we are putting this thing, so let me go to the previous slide. What we're doing is we're putting this thing to here, right, to this part, and we're putting this thing to this part. This is exactly as saying, okay, we are showing this front part here and the back part here, and then we are doing a dot product, right? We are putting basically, and then we have moved a little bit. So after we put it here, we will move it here, and then we will move it here, right? And this is what I was showing you also with this diagram, where we kind of here our input is of 3 depth, right? So the number of channels in the input is 3. So our kernel also has this depth 3, but the height and width, which also happens to be 3, is something we choose. And how many of these cubes we have decide how many of these output channels we will have. And this is what you see here. So so let's go back here. So we kind of, so this is what we are doing, right? So with this first part, so this is our first cube. So this cube that we have, this is our first cube. We can have another such cube, right? And each cube will correspond to one of these output channels, right? Because we take a cube and you move it around the image, around the volume, because the input has channels, and each of this movement will give us this one output channel, right? And then we will take the second cube or the cuboid, and then we will move it around the image, and we'll see that, and that will give you the second output channel. So having understood that, let's look at this, right? So let's look at this step by step. What we are doing is we are putting this here and we are doing a dot product. So 1 into 1 plus 2 into minus 2 plus minus 2 into minus 2 plus 1 into 1, right? Plus, so all this, so this operation gave me 2, right? Because 1 into 1 is 1, and then 1 into 1 is 1, and then no, I think I made a mistake, but you get the idea, right? So it's basically this, and then you will also do a dot product of this. So 3 into 1 plus 0 plus 0 into 0 plus 2 minus 2 into 0 plus 1 into minus 2, right? Because we have kept it on top of this, and then it will give us something, and then we will add it up along with the bias, and in this case we have chosen the bias to be this, and so this gives us this output. Then our kernel, we move it a little bit, right? We move it here, okay? So then what do we get? We get the same thing, right? So we get this minus 2 into 1, so we get a minus 2. Then we get a minus 2 into 2, so we get a minus 4. Then we get a minus 2 into 1, we get again a minus 2. And then 1 into 3, we get a plus 3. So how much is that? So this is minus 5. So we got a minus 5 here. Okay, and then similarly we do it here. So there are zeros here, so only the 2 ones, so the 2 ones have to be multiplied here and here, so we get a 1 here. Then we add it up, so minus 5 and 1 is minus 4, and then we have to add the bias of the first channel, right? The size of the bias is the number of channels that we have. We have 2 channels, and to the entire channel we will just add that bias, right? So we got a minus 4 and then a plus 0.1, so we get a minus 3.9. Let's do it again. So now we have this, so we got a 1 into 2, so we got a 2, plus we got a minus 2 into 2, so we got a minus 4. Then we got a minus 2 into 3, we got a minus 6, and then we got a 1 into minus 2, we got another minus 2, right? So we got a minus 10, and that is what you see here. Similarly, the bottom, you get zeros here, and then there's a 0, so we got a minus 1. So we got a minus 11, and then this positive bias will give us a minus 10.9. And then we keep doing this, right? So we did it here, then we did it here, and then we did it here. Then we moved a step down. So here our stride. So when you do 2D, there can be a horizontal stride and a vertical stride. In this case, the horizontal and vertical strides are 0. Then look at the size of the output, right? The size of the output is the size of your input. So your size of the input is 4 cross 4. Right, and then what is the size of your kernel? It's 2 cross 2. So it's 4 minus 2 plus 1. 4 minus 2 is 2 plus 1 3. So we got a 3. So we got a 3 cross 3 as output. How many output channels? That depends on how many output planes we have in our weights. This is something we choose, and what it means is how many cuboids we have, right? In this case we have 2 of these, right? And this is why your kernels are like this, and then this is something that we are doing this convolution operation with. So you can think of this that we have these multiple kernels, and each kernel leads to one of these output channels. Yes, so we keep doing this, right? So we are just swiping it, and then we got the final value, and then we are done with the first cube. Now it is time to use the second cube, right? And with the second cube we'll do the same operation. We will put it here, we'll put it here, we will slide, and then we will use this bias, right? We will always have these 0.2s here. So then we'll slide it, we'll come down, slide it, come down, slide it, and thus we have our output. We have the 2 output channels completely done, and that's it. That is all that there is in convolution. But then there are certain other additional interesting things about convolution which we will look at in slightly later. So we will look at there is this concept called a receptive window, and then there is this concept of max pooling. The story goes like this. What we usually do is we've done this convolution, right? And let's say we did it with 2 filters. So we got these 2 output channels, right? And then we got, so this is an image, let's say with 2 channels. We call these as feature maps or activation maps, right? Just like features or activations, because it's 2D, we call it a map. And now what you want to do is you want to do this operation called as max pooling. And you can think of max pooling as doing ReLU but in 2D. We'll talk about it, and then we'll also look at it in detail, but it's very simple. And then that reduces the size, and then you do another convolution operation on top of this. And then if you think about it, this second convolution operation, even if your kernel size is small, let's say 2 cross 2, and let's say the max pooling that we did it like we made the size of the smaller one, let's say half of the first one. Then when we now put this, it now looks at a bigger area in our input image, and this bigger area is so-called the receptive field. We'll look at this, but it's good to know, right? It's good to start thinking about the receptive field, and then the max pool operation, and then finally the full convolutional neural network. There is this concept called like dilated convolution, but it's not very common these days, so you can just ignore it, and we will anyways mention it below the video. And that's all that there is in convolutions.